So on page 5 of the notes, we are going to be graphing rational functions, and we will be looking for the following key features in order to graph. So we are going to be using our calculator to sketch the shapes of the graphs, but we will be able to algebraically find these key features. So the first key features that we are going to find are the intercepts. That means both the x-intercepts or the zeros, which are of the form a number and 0, and then the y-intercept, which is 0 and a number. So why do we want to find these points? Well, one, they're not too bad to find algebraically because I'm just going to be plugging in 0. And 2, because they kind of give us some good anchor points on our axis. So those are the first features we are going to be looking for. The second features are any vertical asymptotes and horizontal asymptotes of a rational function, and also the holes. Some functions will have holes, some of them will just have vertical asymptotes. Now, up till this point, we have never had a graph with any type of asymptote before. So let's go ahead and define what an asymptote is. The easiest way I can describe an asymptote is something we approach but never touch. How many of you have a younger sibling? Have they ever pulled that nonsense where they go, I'm not touching you, but they're literally like right there? That's kind of what a function does to an asymptote. It gets right up to it, but never actually touches it. So asymptotes are important because they are going to tell us, 1, the end behavior for horizontal asymptotes, and 2, something about the restrictions for vertical asymptotes and holes. And then step 3, graphing rational functions. I want you to write that we are going to use our key features. So use key features and calculator. So our key features will be our exact points, exact asymptotes, and then we will use our calculator to sketch what it looks like. And folks, I'll just show you some of the answers in the homework. These graphs have a lot of different ways they can look. They can look like this. They can have a few different swooshy sections to them, so very different than any of the graphs we've seen before. A line, a quadratic, an absolute value function, even the nastiest function that we've seen so far, the square root, it is still just kind of one piece. Now, if you're looking at that going, is it a piecewise function? The answer is no. This is all described, these 3 separate pieces, by this one equation. So what happens is these asymptotes create breaks in the functions which segment out the graph. So there's a lot of different ways that they can look, and sometimes the graphs will have holes or values that we get close to but can't actually get due to restrictions. So this is why for these types of graphs, and we do these in pre-calc as well, we have to do a combination of using our calculator, which doesn't always show some of these key features, and algebra skills in order to be able to graph these. So folks, the first thing that I want to explore with you guys is just a parent rational function. So we talked about parent functions way back when we were doing transformations, I think in Unit 2. So the parent rational function looks like this. Y equals 1 over x. It is the easiest rational function that we can have. What makes a rational function? We have variables in the denominator. So rational, fractional. Now, if I told you to graph this, your first instinct would probably be to plug in those 3 favorite values that we used for all of the other parent tables. -1, 0, and 1. So if I plug in -1, 1 divided by -1 is -1. What happens if we plug in 0? We take 1 pi and divide it into 0 pieces. Undefined. And then if we plug in 1, we get 1. So if I were just to sketch out this graph, -1 would be here. And at 1, 1, we would be here. It's like, wow, 2 points to go off of. Not a lot that we can do here. That fact that 0 cannot be plugged in comes from our restriction on our denominator. X cannot be equal to 0. That is the only thing that X can't be equal to. Everything else is defined for X. So that restriction tells me that I am going to have a vertical asymptote, which I abbreviate VA, at X equals 0. So that is the first thing that kind of segments my graph. Now, the next thing I want you to consider is, what if I plug in 0? What can I plug in for X, question mark, that gives me a Y value of 0? Is there anything I can plug in for X to give me 0 for an output? Can't plug in 0. That gives me undefined. If I plug in -1 or 0.5, there is no way for me to get an output of 0. So in addition to having a vertical asymptote at X equals 0, we also have a horizontal asymptote at Y equals 0. So Vex and Hay come back to haunt us. Vex, vertical lines are solo X equations. Hay, horizontal lines are solo Y equations. So I am limited in my graph shape by these asymptotes. I'm going to get awkwardly close swooshing up this way. Closer, closer, closer. Never actually touching that asymptote. And I'm going to curve down this way towards that asymptote. Same on this side, curving up and curving down. So that is the easiest rational graph that I can have. And if you're like, easy, I don't think so, you would be correct. These are very, very complicated graphs to look at because of all the asymptote stuff going on. So folks, we are just going to take it from square one with going through some of our definitions and how we are going to find these. So I actually want to skip the zeros for right now, and we're going to talk about vertical asymptotes. Vertical asymptotes, or VAs, are always going to be X equals equations. And these come from any restrictions on X. So if I look at kind of this general setup for what a rational function looks like, the restrictions are going to come from the denominator. So anything that makes that denominator equal to 0 is going to lead to restrictions. So f of x will have vertical asymptotes when b of x is equal to 0, or in other words, the denominator equals 0. The big thing is that they will always be X equals equations. Now this text kind of got awkwardly cut off on the right side here, but on this side we are going to look at horizontal asymptotes. Horizontal asymptotes are always Y equals equations. Now, these asymptotes don't really come from restrictions, but they tell us about the end behavior, which is what my graph does as it approaches infinity and negative infinity, which is kind of nice. So tell us the end behavior. Now what's cool with the horizontal asymptotes is we can tell using these little shortcut rules what the horizontal asymptote will be based on the equation. And it's all about comparing the degree of the numerator and the degree of the denominator. If the degree of the numerator is, I want you to cross this off and write top heavy. Then there is no horizontal asymptote. So if the degree on the top is larger, there is no horizontal asymptote. For example, y equals x cubed over x squared. If we compare the top degree with the bottom degree, and I can add some constants there as well, we can do 3x plus 5. When we are comparing these, we are only looking at the highest power of the top and the highest power of the bottom. So if it is top heavy, or if the higher degree is on the top of the fraction, then there is no horizontal asymptote at all. If the degree of the denominator is higher, I'm going to cross that off. I just want you to write bottom heavy. So if the bottom degree is larger, then we will have a horizontal asymptote at y equals 0, automatically. And we actually saw this in that parent function. We look at that equation, we've got 1 over x. X is the only variable on the bottom, right up here. So x has a higher degree than the top because there's no variable there. So this is bottom heavy, and that's why we have a horizontal asymptote at y equals 0. Right, Gail?
Yeah.
So moving on to our final one, if the degrees are the same, then we have a horizontal asymptote at y equals the ratio of the leading coefficients. So y equals the ratio of the leading coefficients. So top heavy, bottom heavy, same. So let's say I had y equals 5x squared plus 7 over 2x squared minus 1. If I compare those two degrees, we've got x squared on the top and x squared on the bottom. So these would have the same degrees. And so our horizontal asymptote for this one would be at y equals 5 over 2. So what we are going to do is just first practice these first 3 items. Restrictions on x that lead us to vertical asymptotes, and top heavy, bottom heavy, same, to figure out horizontal asymptotes. So go ahead and turn to the next page. And we're going to start with the horizontal asymptotes, just figuring those out first. So looking at this first equation, is this top heavy, larger degree on the top, bottom heavy, larger degree on the bottom, or same degrees on the top and the bottom? Since we only have an x on the bottom, this would be bottom heavy. And when you are doing the homework, you don't have to write bottom heavy, but this is our note packet. This is what we're going to be doing tomorrow. This is what we're going to be referring back to. And bottom-heavy equations are automatically horizontal asymptote at y equals 0. On the test, you will get to use the list of those 3 rules. Top-heavy, bottom-heavy, same. So we're just going to practice interpreting that based on those 3 rules. So you can flip back to that page in your notes, but you will be provided with that for the test. So looking at our next one. Comparing the degrees or our variable powers, we've got x to the first on the top, and we've got x to the first on the bottom. So is this top heavy, bottom heavy, or same? Same. So then our horizontal asymptote will be at the ratio of our leading coefficients. So horizontal asymptote at y equals what?
0.
2 over 1, which is 2. So this was same. So now we are going to draw these on the graph. Horizontal, think of the sun setting on the horizon. Horizontal is going to be going this way at 0. And we draw it as a dashed line because it's not really part of our graph, but our function itself will approach it. So kind of similar to the bound lines for piecewise functions. Now this one has a horizontal asymptote at 2. So we're going to need to make sure that this one goes through, tick mark 2, this way. So those are our first key features of horizontal asymptotes. On your own, try the next one on the next page. Compare the degrees. Top heavy, bottom heavy, same. What do we think? Same. So we will have a horizontal asymptote at, and we have to write the equation. These are always y equals equations for, hey, y equals 1. And let's go ahead and plot that one. So horizontal asymptotes are all about comparing the degrees. So what this tells me is it doesn't matter all the weird little curves that we are going to have on this graph. As we go out towards infinity, we are going to be leveling off towards this asymptote. Maybe I got a part going this way and a part going that way, but as we go out towards infinity, we are going to be leveling off along that line. So again, it's one of the features that will help us with the shape. So we're going to flip back to page 5 again. And actually, let's just put a giant box around this. Actually, just around these. Will be given for test. So you'll be given those 3 rules. Top heavy, bottom heavy, same, and how we find it. Now, we've said that vertical asymptotes come from restrictions on x or restrictions on the denominator. Wholes also come from restrictions on the denominator. Now, how do we designate a whole from a vertical asymptote? A whole is a restriction whose factor cancels. And I want you to put that word cancels in quotes because it doesn't really cancel out, but we can kind of fudge it enough to figure out where that whole is located. So the formal definition is when there's a common factor in the numerator and denominator, there exists a whole where the factor equals 0 and the function behaves like the simplified expression. Is it lunch? Lunch is at 12:15. Yep, we'll go ahead and stop there and break for lunch.